Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover the last remaining topic of this week, and that is distributed loads. So, in reality, it's very seldom that you'll see a force as just a single force acting at a single point. Force is usually spread over an area. Take flooring in the room, for example. That's spread all over the floor, so it's going to create a nice uniform load pressing downwards on the floor. It's not just a single point. However, if we just treat the loads as that pressure and not a single force, it's very hard to determine things such as resultant moment. And the reason for this is when you're dealing with a moment, you have to have a distance. And if that force doesn't act at a specific point, but is rather spread throughout, let's say, a beam, it's very hard to find that moment arm. So the last part of this week is we're just going to look at distributed loads. And in this class, you'll usually see two cases, a rectangular and a triangular distributed load. And what we're going to do is we're going to learn how to convert those loads into single forces, because that'll allow us to solve for things such as moments and just resultant forces in general. Now, I have to do kind of a quick disclaimer really quick is when you're solving for these forces and you convert a distributed load into a single point load, you can use that to determine things such as moments about the beam or finding your support reactions on a beam, something like that. However, and this is very important, is later on, so not now, but I think a week, maybe 8 or 9, we do something called internal forces. So that's the forces inside of the beam. A load on the outside of the beam would be an external force. Me standing on the floor right now, I'm an external force on the beam. What an internal force would be is, let's say, inside the concrete floor, how the forces distribute within that beam. And those internal forces, you cannot treat these distributed loads as just single point loads. There's a couple of tricks to that, so be ready for that later on. But for now, we're not going to worry about that. We're just going to try and figure out, okay, I got a distributed load. How can I convert it into a point load? And this example will cover both of the cases that you guys will see. So hopefully after this, you guys will be good to go. It should be an easy topic. So let's begin. Alrighty, so looking at this example, what it would like us to do is to replace the distributed loading by an equivalent resultant force and couple moment acting at point A. So remember, in 2D, it's very important which point we take the moment about, because the forces will change depending on the point. And that makes sense because the point has to do with distance and distance has to do with moment. So if we look at the beam, this is what a distributed load looks like. Usually they'll kind of draw it as a square or a rectangle. And what you're going to have to do is convert it into the two. So sometimes they'll give you kind of a composite where it's a square and a rectangle. But if we look at this beam close enough, what we see is if we if we draw a straight line like that, what we actually have is kind of three sections. We have a rectangular distributed load at the bottom. So I'm going to shade that in red here. So we got a distributed rectangular load, and then at the top on the right side we got a triangular distributed load, and then on the left side we have a pink triangular distributed load. So that's kind of the trick to this, is most of the distributed loads can be converted into one of the two types, and that is a triangular distributed load or a rectangular distributed load. So let's go into each one real quick before we start the example and just figure out what we should do. So let's start with the simple case, a rectangular distributed load. Let's say that it looks like this. And it's nice because this will kind of always be the same, nice and easy, so you guys won't have a problem. So usually it's a rectangle, so we draw a rectangle, and what happens is we have a bunch of lines coming down, and they represent the force. So it would be something like this with a bunch of arrowheads. This would be the rectangular distributed load. So just have to draw all these in. So tedious, but yeah, just tedious. No excuses. All right, so another thing that they'll do when they give you distributed load is they'll say the magnitude of the distributed load. So when we're looking at distributed loads, it has forces. It's definitely a force. It's going to have units of newtons. However, that force is distributed along the beam. So what it is it'll be units of newtons per meter, or force per meter, and it lets you know how much force is in 1 per meter section of beam. So let's just take I don't want to do the one up top, so let's just say that this is 10 kilonewtons per meter. So as we see, it's a unit of force, and it's per meter. What happens is too is that of course the load will act over a certain region of the beam. So let's just say that this is 5 meters. So what our goal is to take that distributed force and convert it into a single force acting on a specific spot. So as we can see, the beam is 5 meters long, so let's just draw an equivalent beam. So let's just pretend that this is the beam now. It's still 5 meters long, so I'm going to put 5. And what I want to do is I want to convert that all that force into just a specific point load. So one force that acts at a very specific spot. So the magnitude of the force, and this is very, very easy for a rectangular section, it's equal to the area of the distributed load. So since we have a rectangle, it's going to be base times height, and in this case, it's going to be the 10 times the 5. Because this 10 here, that's actually the height, the magnitude of that distributed load. And if we look at units, what we're going to have here is we're going to have kilonewtons per meter times by meter. So the units are equal to kilonewtons, which is what we want, and the magnitude would be 50. So this would be 50 kilonewtons. So the magnitude due to that distributed load, 50 kilonewtons. That's our point load. But now you have to ask, well, where does this act? And what happens for these point loads, or sorry, distributed loads, is the force will act at the centroid of the shape. So I can't speak right now. The point in the shape at which it would balance. So let's say I put my finger right here on this distributed load. What's going to happen is it's going to start tipping over like this. Makes sense, right? You put your pencil and you put your finger on the very left-hand side, the pencil is going to fall over one way. However, if I put my finger right at the center right here, it's going to balance perfectly. That's the centroid. And we know for a rectangle that the centroid is actually going to be, oops, I'll do something like this. It's going to be the base over 2. It's going to be right in the center, and that makes sense just logically. So what that means is when I have that point load of 50 kilonewtons, it's going to act at a distance of base over 2. So this is going to act right there. We know that this is going to be 50 kilonewtons. And we know that this distance from here to here, that's going to be 2.5 meters. So that's what we want to do, because we know that the left-hand side is going to be equal to that right-hand side. And now when we're taking a moment, let's say about the very left-hand side of the beam, we have that distance of 2.5 meters to work with now. It's not a mystery anymore. So that's the rectangular case. We can do the same thing for a triangular case, and the triangular case is the one that's going to try and stump most people. So what's going to happen is let's just take the same length, and let's just do the exact same as before. So let's just make it a triangle. Let's say that the height at the top here is 10 kilonewtons per meter. And let's just say it acts at, of course, 5 over a distance of 5 meters. So what you guys learned before, or before, when I mean before, I mean 10 seconds ago in the rectangular example, is that the force is equal to the area. So now we just have to say, well, okay, well, what's the area of a triangle? Well, we know that's going to be 1/2 of base times height. So in this case, it's going to be 1/2 of 10 times 5, which is going to be 25 kilonewtons. So finding the magnitude of the force, that's not that hard. We just got to find the the area of the distributed load. So in this case, it'd be something like this. Got to draw on all the points. Now, this is going to be the only real tricky part of this example. Is I know that from a square, just by intuition, if you don't know the math, and that's fine, we're going to learn about the math later, but just from intuition, you know that it's going to balance right at the center point. Now, I know a lot of you will probably go, oh, I know the triangle too. It's not that hard, Clayton. And yes, that's true. It's not that hard. But for those of you who don't know, you're going to have to just kind of memorize this, which is nice. Actually, I think your formula sheet may have the centroid of some shapes on it, which is good. But I'll tell you this now, and you guys will always have to remember this, is the centroid of a triangle is 2/3 from the small side. So it's going to be right here. This little centroid right there. So what this is going to be the distance 2/3 of the base. So if we were to draw that equivalent beam on the other side, so again it's going to go 5, we know that we're going to have the force of 25 kilonewtons, and it's going to act at a distance of 2/3 times the base. So right here it's going to act somewhere like this. This is going to be 25 kilonewtons, and the distance from here to here is just going to be 2/3 of 5. So this is going to be 2/3 of 5. That'll be distance in meters. So same thing as before. If we can convert those distributed loads into just a single force, then we can start taking moments, nice and easy. So this is all you'll have to know for these two cases. We will not give you, let me just go over to Eraser and show you real quick. You will not get a distributed load that's like this, where it's some function. You guys can solve it. It's an integral. It's not too bad, but that's not the goal of this course. We're not testing you guys on math skills. We're testing you guys on just converting simple distributed loads, because realistically, a lot of the forces in real life can be treated as these two cases. Case 1, the rectangular load, well, that's what we do for buildings. We say that the people will have a nice uniform distributed load, something like that. We assume the worst case scenario, so we say that it's everywhere. The second case, a triangle, that'd be a good representation of snow load. So as you guys know, if there's kind of a bank or something, the snow piles up in the corners. Well, that's what the snow would do, something like that. So these are the only two cases you really have to know, but let's try and apply them to this example. So remember, this example wants us to take the distributed load. So remember, as I said, it's not one of these two cases, but it's a composite of those two cases. It can be split into those two cases. And we're going to take that distributed load and convert it into a single point acting at a specific distance. So we're going to take into account moments too. So what I'd like to do for this is I'm just going to draw the beam. So how long is the beam real quick? It is 6 meters. So I'm just going to draw a nice long beam, and I'm going to segment this into sections. So I'm going to go up. I'm just going to draw the support reactions real quick. And we're not going to solve for these support reactions. That's not the goal this week. That'll be the goal next week. So as we look, the beam is split into 3 parts, as I said before. I see that right across the beam, I have a nice rectangular load. So what I'm going to do is I'm going to go up to here, and then all the way across. And yes, I'm going to draw this nice and huge so everybody can see exactly where I'm what I'm doing. So this will be my distributed load like this. Oop, nice and boring. Oh, should I put all the arrowheads on? Oh, you guys are going to be so annoyed. Oh, that'll be fine though. I know that you guys enjoy watching me fail at my artistic side. Alright, so arrowhead. I'm just going to do that for now. You guys kind of get the gist. So this is the first part that I see, and this is going to be the thing that's really going to get you guys when you guys are doing this yourselves, is how well can you see a triangle and how well can you see a square inside of a composite shape. So this is the first one, and we should also label the magnitude of it. So right here we know that this is going to be 3 kilonewtons per meters. Kilonewton per meters, yes. So the next shape that I see is I see a triangular shape on the left side. So it kind of goes up from here, and then it drops down to the center of the beam, which is about this point, perhaps? Yeah. So we see that there's the second one here, like this. And this is going to actually cause a lot of problems for students, and I'll show you guys why when we get to it in a second. I'm sure a lot of you guys can already guess what the problem is going to be, but we know that the height right here is 6 kilonewtons per meter. And then we have the same rectangular load on the other side. Rectangular. I can't even spell shapes, let alone try and teach you guys. Alright, so we're going to have a triangular distributed load on this side. So lots of colors, and this is what I want you guys to hopefully see, is that that composite shape that we had can actually just be split into a bunch of shapes that we already know. And that's going to be very important, especially later on in the course, because we're going to give you crazy shapes and you're going to have to try and see the smaller shapes which you already know inside of it. All right, so what I like to do now is that's what we have, but let's draw the beam again. But this time, let's just start putting in the loads. So we have our beam, and what I like to do to represent those loads on a free body diagram is I'm just going to put a square. I'm not going to put all the arrows this time. I'm just going to put a square of it, kind of a shell of it. So something like this. And what I'm going to do is I'm going to put the force that acts from this just kind of in a more bold way, so it kind of sticks out. So real quick, if we have a square, we know that the force is going to act right in the center of that square. So if we look here, we know it's going to act right at the center, so it's going to be some point like this. So again, I'm making this just really bold to really show that this is where my force acts, like that. So we know that this distance from here to here is going to be the base divided by 2, which we know is going to be equal to 3 meters. And I should probably label this actually up on this side so everybody knows what I'm talking about. So from the question, we already know that this is 3 meters and this one's 3 meters. So from here, we know that that's the force, and I'm just going to label it F1. And right here, I'm going to put F1 is equal to, and remember, it's the area. Since we have a triangle, it's base times a triangle. I really can't say my shapes today. Oh my gosh. You guys are going to wonder how I made it this far and somehow have a degree. All right, so the base we know is going to be the 6 meters, and the height we know is the 3 kilonewtons per meter. So this is equal to 18 kilonewtons. So there, we found the first one. We're good to go. Now, this is where it's going to get tricky for 2 reasons. And let's start with the red one because it's a little bit easier than the next one for one very, very specific reason. But let's go to this one. So remember, the force acts at a distance of 2/3 from the small side of the triangle. So this is kind of an interesting case because it's reversed. The small side is actually on the right side. So we know that this force is actually going to act somewhere right here. And I'm going to put this force as F2. And remember, we always want to try and keep all our distances measured from the left-hand side of the beam. So we're looking for this distance. And instead of that being 2/3, we know this is actually 1/3 of the 3 meters, which is equal to 1 meter. And the reason why it's 1/3 is because we're measuring from the big side of the triangle, the tall side of the triangle. Remember, the centroid is 2/3 from the small side of the triangle, so from the far right side on this in this case. And from here we can go F2 is equal to, it's going to be the area, so we know the area of a triangle is 1/2 base times height. So it's going to be 1/2. We know the base of the triangle is 3 meters. And now this is what's going to trick a lot of students, which is going to cause a lot of problems if you guys aren't paying attention correctly. Is they're going to look up here, and then they're going to say, okay, well, we got 6 kilonewton meters. Well, it's 6. The height is 6. And that would be incorrect. When we're looking at the height of the triangle, we're looking at this relative height right here. And that right there is going to be the 6, which is the total height, minus the 3 from the rectangular distributed load. If we were to put 6 in, we're counting for loads that's not even there. So, come down here. We know that this is actually going to be 3, not 6. And that is one thing that'll get a lot of students, is they'll put 6 there. And what we'll get is 4.5 kilonewtons. So, that's good. Now we can do the other side. Comes up to here, nice and easy. This one will come down, and we know that this one's going to also be 1/3 away from the big side. But remember, our whole goal is to try and get all these distances relative to the very left side of the beam. So in this case, we're looking for kind of this distance all the way from the left side of the beam to the force. And we know that that's going to be equal to the 3 meters. So that's just to get to halfway to the beam. And then plus 2/3 of the 3 meters, which is equal to 5 meters. So again, for the 3 meters, that's just to get from the left side to the center of the beam. And then we add the 2/3, which goes from the center of the beam to the centroid of the triangle. And of course, we can figure out the magnitude of F3. F3 is going to be equal to 1/2 of the base times height. And it's actually lucky because it's the exact same as before, so we can go 1/2 of 3 times 3, which is equal to 4.5 kilonewtons. All right, so now we have all of our distributed loads conveniently in 3 separate forces with 3 specific distances. So if we're looking for the resultant force of all this, well, we can just add them together. We know that Fr is going to be equal to 18 plus 4.5 plus 4.5, which is equal to 27 kilonewtons. Okay, well now we're really getting somewhere now. We're working fast, and the only thing that we have to do is we have to think, okay, well, what moment does this create on the beam? So we have to try and go through and think, okay, well, this is going to create a moment. So if we were to go sum of the moments and it wants it at A, we're going to have to just go through these and find the moment each one creates. So let's start with F2 because it's closest. We're going to have F2, which is 4.5. And we know the distance from F2 to A, which we solved for, and we know that that's 1 meter. And now we also have to look, okay, what kind of moment is that going to create? Well, if we look at the direction, we can see that it's going to start creating a clockwise rotation at about point A. So it's very important you know which point. So about point A, it'll be a clockwise rotation. So we know that this will be a negative moment. And then all of them, we can kind of see that they're going to create that clockwise rotation because they're all in the same direction and all on the right side of point A. So we can go minus, and then the next one would be F2, which we know is 18. And the distance here is going to be the 3 meters to point A. I'll just label point A real quick. And we're going to go minus 4.5. And now we have to find the distance, which we have as 5 meters already. So we can just go 5. So we know that the moment, or some of the moments at that point, is going to be negative 81 kilonewtons times meters. So we replace this system with a resultant force of 27 kilonewtons. And we should put that's downwards. And then there's also resultant moments due to these of negative 81. Actually, we're just going to put 81. So you can put negative 81 or you can put 81, but I'm going to put 81 kilonewton meters. And I'm going to specify the direction as clockwise, which is why I put it as positive. So that's the final answer. But now I know a lot of you guys are going to ask me real quick. And this is some, oh, that's a terrible box. All right, that's a much better box. A lot of you guys are going to say, okay, well, you just sum the forces about moment A, or you did some of the moments, and you didn't put, actually I'll do this in a different color so you guys know what I'm doing exactly. I'll erase this, I'm going to go to pink, and you go, okay, well, shouldn't it be equal to 0? And you're right. If this beam is in equilibrium, all those forces will equal 0. All the summation of all the forces will equal 0. So now you're going to look, okay, well, it has to equal 0 at some point. So if I sum the moments about A, well, the negative 4.5, that's definitely there. The negative 18, that's there. And the other 4.5 is there. So I'm getting a bunch of negative moments. I know that that answer is not going to be 0, but how can it be equal to 0? Well, remember, the goal of this example was just to find the resultant force and resultant moment due to these external loads. Later on, which is next week, when we analyze these beams, we're going to have to take into account all the loads. And by all the loads, I mean, okay, well, we have the external distributed loads, but what's counteracting them? And those are the supports. So realistically, this is a pin at A, so we would have a vertical force there. There's a roller at B, so there'd be a vertical force there. And then, of course, there's a pin at A, so there's a horizontal force. But as there's no forces in the x direction, we can see that's 0. But those horizontal reaction forces are what's going to create that equilibrium. If I were to sum the moments about A, I see that this, I'm just going to call this AY, and this one will be BY. If I were to sum the moments at A, we know that AY is going to be 0 because it acts right at the moment point. The distance is 0. However, By will create a moment. So if I were to go back to this equation and I were to go sum of the moments at A and I want to include everything, it would be plus By times the distance to By, which in this case is 6 meters, is equal to 0. So from there you guys can say, oh, well, I have that equation. I know it's equal to 0 and there's only one unknown. So if I really wanted to, I can solve for that reaction force By real quick. And that's what we're going to do next week, is we're going to use these sum of the moments and equilibrium to find the reaction forces at B and the reaction forces at A. And that's going to be such a huge part of this course going forward, because trusses, you're going to have to find reaction forces. After trusses, we go to beams, and in beams, you're going to have to find reaction forces. So this concept is very, very important, but right now, again, we're just focusing on creating those distributed loads into specific point loads at specific locations, and that's it. And we did that, and we found the resultant force and the resultant moment. But realistically, this middle diagram there with the F1, F2, and F3, that's what's going to be important for you guys moving forward, is just creating those diagrams in your free body diagrams. So that concludes this example, and I guess this also includes this week. So next week, we're going to get into those reaction forces and try and figure them out. But it's actually really easy, so you guys got really nothing to worry about. However, after that, it's going to start getting more and more real and more difficult. But lots of videos to come, so don't worry, don't be scared. You can be scared later. All right, so thank you all for listening, and I'll see you guys in the next video.